Improving the imaging depth of optical microscopy has been a long-standing goal in the field of bioimaging. While imaging with light provides good enough resolution for observing from tissues to cells, cell organs, and even some molecules, imaging capabilities experience severe difficulties when imaging thick, highly diffusive biological structures. One of the main reasons is the optical phenomena called multiple scattering, which obscures the so-called ballistic wave that carries object information. When light propagates through transparent medium and hits a target, a sensor can collect the exact information carried by ballistic photons. In an ideal imaging condition, an image can be reconstructed from every point of the target object. However, when light passes through scattering medium such as biological tissue, we cannot know which signal is from our desired target, thereby making it difficult to reconstruct an image. In general, the intensity of scattering component is inversely proportional to the depth of a sample, but the intensity of ballistic component exponentially decreases as the scattering mean free path of a sample increases. The scattering mean free path, L_s, is an optical property. Usually, biological tissues have a few hundred micrometers of L_s. There have been several attempts at extending the imaging depth, such as various gating operations and use of ultrasound modulated light. As explained earlier, we need to gain more ballistic signals and less multiply scattered signals. Blocking such undesired components is therefore called gating. There are several gating techniques such as confocal, time, and polarization. Especially, time gating reduces multiple scattering signals by using the difference of arrival time, as the ballistic components will undoubtedly have the shortest path length. Another technique is called ultrasound modulated optical tomography, which uses an ultrasound focus with high frequency that modulates the optical frequency of light. Since sound wave can penetrate biological tissues without much degradation, it acts as an effective guide star for detecting light, due to an important phenomenon called acousto-optic interaction. However, despite its penetrating depth, such technique does not have a high resolution compared to other optical imaging methods. Whenever a sound wave propagates through a medium, it varies the material's permittivity due to mechanical strain. It is in fact a special case of photoelasticity, which is a change in the optical properties under mechanical deformation. In such variation, the material now acts as a grating for propagating light. This means the light experiences diffraction with frequency modulation. Our new technique called space gating is based on this effect, making use of ultrasound focus on the target plane as a spatially gating window. This dramatically reduces multiply scattered components which do not pass through such window in which ballistic components are dominant. For our detection to work at its best, we use holographic phase microscopy with an acousto-optic modulator and an ultrasound transducer and observe through specifically fabricated sample tray. In order to prove the performance of our technique, we provide a useful factor called noise suppression ratio, which is an estimation of improvement over the noise due to multiple scattering. Such factor increases up to 100 times better as the total optical thickness increases, where we used a light-absorbing target embedded between front and rear scattering media. Without space gating, the results show that the images suffer from severe degradation, whereas the same images with space gating contain the objects that are clearly visible. To prove the effectiveness of space gating, we demonstrate non-invasive and label-free imaging results of biological samples. The first notable result is the phase image of red blood cells within scattering media. The cells are clearly visible on the right where space gating is applied. The other result is the intensity image of zebrafish muscle fibers. Especially, we acquired the large field of view image with high resolution of optical imaging. The scale bar of the images E to J is of 10 microns. Summary. In order to image inside a highly diffusive media such as biological samples, we have to overcome the noise due to multiply scattered light. There are several techniques for reducing, gating, multiple scattering components such as time gating and ultrasound modulated tomography. We demonstrate a new technique called space gating, which uses acousto-optic interaction of light. This technique successfully suppresses the noise, which makes it possible to image within biological tissue. Further development of space gating will provide an important step toward reaching the ultimate imaging depth set by the detection limit of ballistic waves.